Hello, my name is Guy Beals, and I am here today to present my project summary for my implementation of a text processing pipeline using natural language processing. I built this in Python using a producer-consumer pattern along with multi-threading and two queues. Here is a high level of the presentation. We're going to touch on each one of these slides as we go through, and if there's time at the end, we'll go ahead and do a quick demo of the code. Just as an introduction to the research paper I wrote around this, which can be found here on Medium at Guy Codes, Guycodes. The overall objective of the paper was to focus on the implementation of a text embedding model, namely the E5 Large V2 on Apple Silicon, particularly consumer-grade hardware, through the use of optimization techniques. Now, just a little bit about my background. I'm a software developer working with natural language processing, and we were targeting the use of the E5 Large V2 off Hugging Face. And just as a summary, we did find that there were substantial improvements in accuracy through some of our optimization techniques, particularly by allowing the model to work on consumer-grade hardware. Such strategies were really paramount to the success of this project in order to get some of these models that in the past have been, somewhat prohibitive for consumer-grade hardware to actually run and not sacrifice, with model performance in other areas that could reduce, its overall accuracy. Now, the importance of text embeddings and natural language processing is pretty central to the concept of natural language processing, in that text embeddings allow for these large language models to have a better understanding of language by turning the text into vectors, which are numeric representations of the text. This improves the model's ability to extract relationships, understanding, and overall context to really provide a greater benefit to the user with computing optimization and use of less resources. Now, the historical background, some models in the past have not really been useful on consumer-grade devices like Word2Vec, but they have set foundational benchmarks for the text embedding space. And this has kind of brought to light that there is sort of a gap with some research around text embeddings on Apple Silicon devices. A lot of research has been done using PyTorch on like NVIDIA backed devices using CUDA cores, but not nearly as much has been done on these Apple Silicon devices with the metal performance shaders. However, regardless of the platform, PyTorch still is central to the integration and use of text embedding models, as it kind of provides the interface for interacting with the GPU support on these devices. Just to even use PyTorch, it's worth mentioning that some patching needed to be done on the E5 Large V2 to bring it up to date with current versions of PyTorch, which interestingly enough did net about 1,000 downloads within the first month of me patching it, which you can find over on Hugging Face. My Hugging Face is just going to be Guy Morgan B. Now, we did implement some text normalization techniques in our pipeline, including lowercasing, punctuation removal, and tokenization consistency. We used the Hugging Face tokenizer to kind of create a consistent environment with how we were tokenizing. as well as batching strategies. We did implement a dynamic batching strategy, so the batch size could dynamically change based on the text corpus that we're trying to consume. We also implemented some data structures and some programming patterns, as well as some multi-threading to increase overall efficiency and optimize the environment for use on consumer-grade hardware. So in this case, we did use a observer pattern to watch some files, and we used a producer-consumer pattern when we worked through implementing multi-threading to be able to consume multiple files at once and efficiently work in a parallel processing environment to also optimize resource. Now, the text embedding pipeline was tested on textbooks that were up to thousands of pages long, and it efficiently processed multiple of them simultaneously, so it was working pretty well. However, I would not recommend doing that on devices that do not have GPU acceleration. I would recommend sticking to more run-of-the-mill everyday documents that you might run across, like what we're going to hopefully show an example on here shortly. Now you can find the repository with all the code here, Guy Codes with 2 Y's on GitHub. Now, vector similarity. Let's talk about vector similarity briefly. So vector similarity is what we use in our vector database. In this case, we use Quadrant. And vector similarity is basically, in the case of cosine similarity, the measure of the angle distance between two vectors in vector space. And this is going to allow us to get an idea of how similar or different the text phrases that have been turned into vectors are based on the angle measurement that we take here using cosine similarity. And the great thing about Quadrant vector database is this is a setting that we're able to set, and it takes care of a lot of that computation for us. This type of searching provides real-time querying and optimizes the user experience as well. Now, the experimental setup that we used involved 2 computers. We had a MacBook M1 Pro with 16 gigabytes of RAM and 1 terabyte hard drive. That was a regular entry-level consumer-grade device. And then we also had a MacBook M4 Max, which had 128 gigs of RAM and 8 terabytes. Each had different levels of GPU acceleration as well. And the performance measures were measured using tokens per second, memory usage, batch size, in order to assess the model efficiency on the MS Marco dataset, which was put out by Microsoft. Ultimately, we achieved a Spearman correlation of approximately 0.86, indicating that we were receiving some high-quality embedding results through our optimization. The overall optimization techniques were absolutely essential to achieving the results that we did, and we'll go ahead and take a look at some of the performance comparisons here between the M1 and M4, which differed significantly. Throughput gains alone were about a 30% difference between the M4 and the M1, and the inference efficiency was significantly different at about 25% as well. And depending on the text that we were running inference on, as well as the text we were consuming, these could even increase from here. Now, in conclusion, there are a couple key takeaways here. That we can, through optimization techniques in our code, make some of these more resource-heavy tools operate on consumer-grade devices. This is a testament to some of the drama in the tech world we've seen around DeepSeek and how they were able to implement that setup at a much lower cost than some of the things that OpenAI has done. And so this really brings to light the crucial nature of efficient programming and implementation processes. Now we can view our data set here in all of our calculations by following this link to Google Doc. And I have about 1 minute, so let me go ahead and briefly run through an example implementation that will coincide with the README document for anyone interested in implementing this on their own. So let's go ahead over here, jump into our code, and first we're going to make sure that we have Quadrant running. So I'm going to check here, in my Docker desktop, and I have Quadrant running right here on port 6333. I also check Quadrant here by putting this, which is in the README, my URL bar. I can get a visual representation of Quadrant in the browser. Now, I notice Quadrant was empty, it has nothing in it. What we're going to go ahead and do is we're going to go ahead and start main.py. We're going to roll over here to the root of our project directory, docs pipeline 311. Start up main.py. It's going to check and make sure that Quadrant is running with the health check. It's going to do a few other things. Start up a couple thread processes with some workers. And then once that's all set up, we can go ahead and find a document we want to embed. So I'm actually going to embed the structured data and inference in deep QA document from IBM's Watson project, which is certainly related to the implementation that we have here. I'm going to grab this document and I'm just going to drag and drop. You can also use command line, but the point is here that we want to take this document and move it into our dirty documents folder and move it over to the PDF file because it is a PDF, drop it in the PDF, and we're going to watch the pipeline sense that it changed and it's going to take off. So it's performing NLP right now, going through the document, chunking everything, and now it's chunked it all out and it's going to send it to the vector store. Looks like we got a success message and we got 36 chunks sent over to document vectors in the vector store. Let's go ahead and refresh. Check that, we got our 36 points. We have our cosine similarity search set. We want to make sure that we have our vector size appropriately matched to what we have set with our embeddings model. Now we're going to go ahead and we're going to start the CLI tool, which is configure.py, and we're going to go ahead and look at our output in clean docs. This is our chunked text. Now we're going to go ahead and try and find something that might be a good query. Let's try here on line 17. Now we're going to go back to our CLI and I'm going to select test query model. It's going to warm up the query model. So if you don't have one set up already, it might download one. You can change that in the settings as well. If you look into the config.yaml here, there's going to be a lot of settings you can change, but these are also dynamically adjustable through the CLI. We're going to do a deep semantic search because the deep semantic search is actually going to give us some scoring results. And I'm going to take this text that I just got from the chunked results. I'm going to turn it into a question. So what are what are two important aspects of the TIE-core problem? So we're going to hit enter. It's going to search the vector store for similar results and give us some scores. It's going to return the top K results, but in this case K is 5, so we're going to get 5 results with scores. Looks like our search results yield a 79.71 similarity score for passage. Two important aspects of the TIE-core problem are mapping the textual mention of a candidate answer to an entity resource in a structured knowledge base and matching the lat of the question to a class in a type system or ontology. So that seems like a pretty close candidate answer to what we're posing as a question. And we could go through and read more, but that's going to wrap up my presentation. Feel free to engage this code on GitHub, and if you find any ways to improve it, let me know. Thanks.